Welcome back, everyone. We will continue today with our first unit in the course, which is on solving linear algebraic equations. The example I gave you last time about that nest fire, that's an example from a method called computational fluid dynamics or computational physics, where you solve these complex equations of fluid flow and heat transfer and all those great things. You solve them on a computer. To do this, there's a process called discretization, etc. We will learn about it. I will teach it to you in this lecture or next lecture when we do it in 1 dimensions, and then a few months down the road how to do it in 2 dimensions. But the point I want to drive here is that in all of these situations, you will end up with a system, with large systems of equations, linear or nonlinear, that you have to solve together to find, for example, the temperature distribution, the velocity distribution, the pressure distribution, and so on. Okay, we will do an example on this, I promise. But for now, our focus is going to be on how to solve systems of equations. Again, the first part of the course, if you remember, I want to equip you with some tools, some computing tools, so we can solve practical problems once we get to a little bit more advanced stuff, and getting you ready for your next semester when you're doing transport. Okay, so first the question is, what is an algebraic equation? Obviously, I'm trying to distinguish here between algebraic and differential equation. So an algebraic equation is not a differential equation, but I want a more specific definition, or you have to define what a differential equation is. So what do you think an algebraic equation is? Well, differential equations are also the same. You're trying to solve a specific quantity, right? Isaac, you had an idea?
An equation where something is defined by an association of dependent variables without any difference in variables required.
What do you mean difference?
So an equation where you have z is equal to x plus y, where x and y are dependent variables, and nothing like z is equal to dx over z.
Okay, so the derivatives. So yeah, derivatives. Yeah. So any equation that does not involve derivatives for your unknown, the quantity that you're looking for. What's the quantity you're looking for? You might be looking for temperature, or velocities, or pressures, or concentrations. Those are unknowns, those are variables. They depend on other quantities, etc. If the equation that governs your system contains derivatives of those functions, or integrals of those quantities, then that's not an algebraic equation. It's a differential equation, or integral equation, integral differential equation. Anything that's not that, we generally colloquially call an algebraic equation. It's one where there are no derivatives or integrals of the unknowns. When only derivatives are involved, the equation is called differential equation. So here's an example. This is an algebraic equation. Here, the assumed unknown, or the quantity of interest, is u. That's u squared plus cosine u equals 7. That's an algebraic equation. There's no derivatives in it. There's no integrals in it. This, for example, is a differential equation. It's a first order ordinary differential equation. We will learn those a little bit later, how to solve them numerically. But this is not an algebraic equation. Okay, you have to do other solution techniques. So this is an important classification, because methods to solve this are a little bit different than methods to solve these. Although, eventually, when we're working with differential equations, we will end up with algebraic equations, but we need one more step. So what we will do, if we learn how to solve algebraic equations, once we hit differential equations, we will first convert them to algebraic equations, which we know how to solve, and then solve them. Right? So there's one more level of complexity and abstraction with differential equations, and eventually we will convert them to algebraic equations that we need to solve. So let's learn how to solve algebraic equations. Okay? Now, algebraic equations come in 2 flavors, and this is a definition from the perspective of engineering, not pure and applied mathematics, from the perspective of engineering and computing. What is a linear algebraic equation? So now we're working with algebraic equations, and in this chapter we will be working with linear algebraic equations as opposed to nonlinear algebraic equations. So what's a linear equation? What's linearity, in other words? You see an equation, can you tell if it's linear or not? How can you tell if it's linear or not? So I'll give you back this one. Is this equation linear in U or not? Why? Okay, so there's it's to the power 2. What if I had U plus cosine U equals 7? Would it be linear? Okay, so you have an intuitive feeling of what a linear equation should be like. More specifically, a linear equation is where your unknown, or unknowns, not other parameters. I might have parameters that are controllable by the user, for example, like the length of a chamber or the flow rates, right? Those are not dependent quantities, they're controlled quantities. They might show up under squares and cosines, but you're not solving for them. The quantity that you're solving for is what you're trying to assess whether it is linear or not. So in general, when the quantity you're solving for, which you call the unknown or the dependent variable, as we build our knowledge here, we're going to call them dependent variables, where it shows up linearly. In other words, it's neither squared nor operated on by any transcendental or complex function like sine, cosine, exponential, logarithm, square root, all of these things. A power of 2, a power of half, a power of 3, any of those make it nonlinear. So for example, all of these equations are linear in x. I have square root of 2x plus 3. Although there's a square root here, the square root of 2 is just a number. You know it. It's not an unknown. You're trying to solve for x. X is your unknown here, or quantity of interest. Here's another equation. Ax equals c. A and c are parameters. You control them. They're like maybe the length and width of something, right? And you're trying to find this unknown x. This x shows up linearly. It's x to the power 1. That's it. It's not under a log or a cosine or sine. 2x equals 5, another example. These are examples of equations that are nonlinear in x. 2x squared plus 3. I'm not asking whether you know how to solve it. Yeah, you can say here x squared is minus 3 over 2 and you have a complex solution here. But that's not the question. X squared, it makes x show up nonlinearly. A square root of x equal b. You could say, well, you know, if I take the square of this equation, it makes it linear. It becomes a squared x plus b squared. But still, the way it's presented, x shows up nonlinearly in this equation. The relation between x, a, and b and everything else is nonlinear because x is to the power 1 over 2. 2 log x, same thing. So the thing you need to be focused on is the unknown. Does my unknown show up linearly or nonlinearly? If there's one term, if there's 50 terms that contains the unknown, and one of them is nonlinear, that's it. That makes it nonlinear, okay? Now, for the rest of this unit, I'm going to drop the word algebraic. I'm going to say linear equation, and I'm assuming I mean linear algebraic equation as opposed to linear differential equation. Okay, later on, once we hit differential equations, we'll do the same. We'll call the differential equation linear equation or nonlinear equation. But because we're working with differential equations, you'll know we're referring to the differential equation. Here, all the equations, when I say the word equation, we're referring to a algebraic equation. All right. Now, you know how to solve a single linear equation, ax equal b, and then x equal b over a, and that's easy. What we're interested in here is solving systems of linear equations. What's a system of linear equations? It's when you have 2 or more unknowns, 2 or more variables that you want to solve for, and each one of those variables show up linearly in all of the equations. Okay, you could have 1,000 equations. If one of them and one of the unknowns shows up nonlinearly, you have a nonlinear system of equations. Even if all of them, most of them, if 99 of those equations are all linear and all the unknowns, if one of them contains one unknown that shows up nonlinearly, that makes the system a nonlinear system of equations. Okay? Here we're dealing with systems of linear equations, so all the unknowns show up linearly. What are the unknowns here? X and y, an example. and x shows up linearly, y shows up linearly. It's not powered, it's not under a transcendental function or any weird combination of x and y, like y over x, for example. It would make the system probably make it nonlinear if you cannot arrange it in a linear way. Now, why do we deal with systems of linear equations? We need to learn their solutions. Why do you take linear algebra in high school or like first year of college? Because they show up everywhere in engineering. And what's frustrating is that you go and learn linear algebra and you study the theory of linear algebra and the existence of linear algebra, and you never make the connection with, as students, myself, I never made the connection between linear algebra and like when I took circuits in electronics, or when we started doing conservation of mass in fluid mechanics. I never made the connection that these are systems of linear equations that we studied in math. So I'm not going to go into the theory of linear algebra. I am going to use what the mathematicians have already proved to be true and correct, and we're going to run with it because we are engineers. We're interested in using what the mathematicians discovered to solve linear systems of equations. Okay, now where do they show up? They are all over the place in engineering. In almost any situation you will see in your career, and especially if you get into computing or you're trying to model systems that are highly nonlinear, whether differential equations or algebraic equations, you always convert any system to a system of linear equations. So it's like at the most fundamental level, any solution we need to get, even when we say we're solving a nonlinear system of equations, the solution process involves solving systems of linear equations over and over again. So learning how to solve systems of linear equations effectively and having the tools to do that is very important. All right. So in CFD, computational fluid dynamics, it's very ubiquitous. Almost always we deal with systems of linear equations, especially the pressure. I've had 3 PhDs work on this problem just for the pressure, because the linear system for the pressure, it's very, very large. It's very costly to solve, as I will show you later. These can be very costly to solve. Even they're linear, but when you're talking about a million equations, or 10 million equations, or 100 million equations that you want to solve simultaneously, it becomes really expensive to solve them. So we have a couple of PhDs working and who have already worked on trying to solve fluid dynamics without solving for the pressure. So trying to get rid entirely of that system of equations and approximate it without solving the system of equations. Anyway, so it's a big deal. Data analysis, you'll see when if you're doing neural networks, you will end up with large systems of we're trying to do regression for these parameters. Like ChatGPT in the original version, it had 1.8 billion parameters that needed fine-tuning. So they needed to solve to optimize that system to find the regression for all the trained data. They had to solve a system of 1.8 billion equations to find those parameters just to be able to fit that neural network. Okay, so this is real stuff, important. It's not esoteric or just speaking in the clouds. Okay, we will start with conservation of mass. I told you that I'm not going to do physics here, but I want to kind of push you a little bit in that direction to get your brain thinking. And you actually got yourself in trouble for this, because in the intake survey, 100% of the answers said that they know conservation of mass and they know how to write it down. Okay, so I'm going to hold you accountable for that. All right. So one of the most important principles in engineering, in physics, in nature, is conservation of mass. Essentially saying mass cannot just disappear. Okay, you bring in mass into a system, it has to leave somewhere or it has to stay in. It might evaporate, it will turn into something else, but you have to account for that. It doesn't just suddenly vanish. Okay. The principle is expressed as a mass balance that accounts for everything that's coming into your system, or think of it as a bucket. I describe it here as a volume. You might think of water. You're bringing in water, and then some of it is accumulating, some of it is leaving, right? You might open the faucet over there. You might have more coming in, less coming out, etc. Okay. So now I'm going to ask you, because you said in the survey that you know how to write down mass conservation. So I want you to write it down for this system. Use the word accumulation, input and output, and write me, just go grab a paper or your notepad, whatever you're writing on, and just express the principle of mass conservation for this system. Again, think of this as a bucket. There's water coming in, there's water leaving, and some of it is accumulating. Write down mass conservation. And it doesn't matter whether you're coming from chemical engineering background, from mechanical, from physics, from chemistry. This is a guiding principle for all the sciences and engineering. And you also said you know how to do it, so. So I want you to write down the relation between accumulation, inputs, and outputs, okay? We have any answers? You can just tell me. You can just say it.
Okay, so it's mass in, mass out, reaction, which is not here.
No, just for this system.
Yeah, and accumulated mass equals accumulated mass.
Okay, so what did you say? Inputs,
Mass input minus mass output.
okay, equal accumulation.
Yeah, but the accumulation depends on the volume of the track.
How
So
so?
if it's like a closed volume, there is no expansion, then it's like,
Doesn't matter.
just like geology.
Doesn't matter.
Or the space, right?
Yeah. Okay. So anybody else? Relation between accumulation, input, and output. What is the relation? We had one answer. Do you at least agree? Do you disagree? Okay. So, okay, I agree. Accumulation is equal to inputs minus outputs. Okay. So think about it. You have a bucket of water. It has a little faucet. You bring in a certain flow rate, 1 kilogram per second, and then you open the faucet. It's taken out 0.5 kilogram per second. So there's some accumulation that's going to stay in there because more is coming in than leaving. Okay. So now I'll ask you, why input minus output rather than output minus input? That was another question on the survey. When I told you the flux of mass coming in is negative and the flux of mass coming out is positive. 30% said, I have no idea what that means. 30% said that's true. 30% said that's wrong. Okay, so we're going to learn that later when we get to vector calculus. But here, assume input is a positive number, output is a positive number, accumulation is whatever results. Okay, so input could be 1 kilogram per second, output could be 0.5 kilogram per second. Why is it accumulation equal input minus output rather than output minus input? Critical thinking. Yeah?
Isn't it just kind of deciding whether we're actually accumulating or whether we're losing what we've already accumulated in the system? So like, if we had a bucket of water that was already full of water, and then we have a spout where we're pulling some off, and we're adding some back into the bucket. If we've increased our nozzle out more than we put in, the bucket level is going down.
Correct.
So
the accumulation, the rate of accumulation needs to go negative.
Yeah.
Okay. So what your colleague is saying, the reason is that we want accumulation to be positive if we're putting it more than we're taking out. That's our convention in life, that things are positive when they are increasing. So if we're putting in more than we are taking out, accumulation needs to be positive. So if inputs greater than outputs, that gives us that. What happens when output is greater than input? Accumulation is going to start decreasing. So if you had an initial level in the water and you open the faucet 1 kilogram per second and you're putting in only half, well, that accumulation is decreasing over time, right? So it's negative, and that's consistent with our convention in life. So, okay. Anyway, so bear that in mind once we get to vector calculus, because the inputs are going to be negative because of vectors and stuff, but then we'll make them positive by moving them to the right-hand side. So this is the algebraic form of the true mass conservation law. Okay. All right, so we explained that. Now, at steady state, when there is no accumulation at all, like the level of the water in the bucket is frozen. It doesn't go up, it doesn't go down. It means whatever is coming in is leaving, exactly. We call that steady state. Okay, so if you put in one, let's say you have a bucket, or that, I don't know why we stuck with that example. Okay, we have a system, it has, water like 0.5 meter high. Okay, and then you put in a hose on the left that's bringing in 1 kilograms of water per second, and you open the faucet on the other side that's drawing 1 kilograms of water per second, then the level of water in the bucket is not going to change. So accumulation becomes 0, or the rate of change of what's coming in and leaving is just 0. So in that case, we call that steady state, and we therefore say that inputs equal outputs. Whatever you're bringing in must leave. Okay, whatever you're bringing in must leave. Okay. We'll start with an example which you will apply in your homework. I already put in the homework on Canvas, so you can take a look at that. Okay, so this is a steady state reactor system that you've learned maybe in chemical engineering or in your studies in physics or chemistry, where we're bringing in a compound at 2 different concentrations. Okay, so concentration, mass per unit volume, so these concentrations C1 and C2, kilograms per cubic meter in standard units. And flow rates, we designate those as Q. The flow rate is how much, or volumetric flow rate, how much volume of fluid are we bringing in per second. So typically, the volumetric flow rate is given as Qs in cubic meters per second. So it's a rate per second. And the concentrations are mass per unit volume. The product of the two, so if you multiply meters per cube per second times kilogram per cubic meter, you get kilogram per second, which is the mass flow rate, what you're interested in. So when you're thinking mass conservation, you immediately have to think kilogram per second. It's mass per second, mass per unit time. So when I multiply flow rate in cubic meter per second times concentration in kilogram per cubic meter, I get kilogram per second. So that gives me whatever mass is coming in from this pipe. There's another mass that's coming in from this pipe. It could be a different flow rate and a different concentration. They're getting mixed here somehow. Okay, they're getting mixed somehow. And the system, we say it's steady state. And this is where it's leaving at this flow rate and this concentration. Then the mass balance tells us inputs must be equal to outputs. In other words, C1Q1 plus C2Q2 equals C3Q3, right? Very simple. Whatever is coming in must leave. The mass that's coming in must leave. This is the mass input. You could have 50 of those. You just add them up together. Okay? They add up linearly. Okay? So kilogram per second equal kilogram per second. Okay? All right, so let's do a practical example so we can just kind of start working with an actual system. This is a slightly more complex example coming from separations. I have an initial stream coming in here at 5 cubic meter per second with an initial concentration of 10 kilograms per cubic meter of some compound. It enters this bucket 1, okay? Now, immediately, because we are steady state, we assume that everything mixes really quickly, or these buckets are small enough that where there's a stream coming from here, so the concentration of the compound in this bucket, there's one compound everywhere, okay? But the concentration of the compound in this bucket becomes C1. I don't know what it is. Why? Because I'm bringing in some of this concentration over here. It's mixing with this concentration. Some of it is leaving. So I don't know what the concentration is going to be here. That's actually something I want to find out as I design my system. All right? And then out of this system, there's a pipe at a volumetric flow rate of 3 cubic meter per second. And it comes into this bucket. Some of it is taken out, okay, at 2 cubic meter per second. And some of it, so we call this concentration 3, some of that goes to this bucket 2. Okay, flow rate here, 1 cubic, you can control those usually. 1 cubic meter per second, it goes into this bucket 2. Some of it is drawn out, okay? Well, some of it is drawn out at 3 cubic meters per second, and some of it continues here, okay? So these are the volumetric flow rates, and you only need here just this initial input stream concentration. So first we ask ourselves, okay, what are by known quantities. I know all the volumetric flow rates. That's really good because then mass is simply concentration times flow rate, right? So for example, the mass that is coming in here is Q1 times C01, or 5 times 10. That's 50 kilogram per second coming in here. What is the mass that's coming in here? It's Q4 times what? C2. C2, there's only C2 coming out of this bucket. So C2 is coming here at a rate of 1 cubic meter per second. So you get Q4 times C2 kilograms per second coming in. Now, the known quantities are the volumetric flow rates and this initial concentration here. What are my unknowns? C1, C2, and C3. That's what I'm looking for. I'm designing the system. This setup like this. I want to know what these concentrations are. Okay, so I want you now to derive, okay, we have 3 unknowns. I want you to derive the equations that govern these unknowns. I'll help you with the first one. So for bucket 1, we said at steady state, and this is all at steady state, inputs equal outputs. Okay, forget everything else. I have bucket 1. What's coming in? Q1 times C01, or 50, plus Q4 times C2, right? So that's what's coming in. And there's nothing else coming in. And there's only one thing leaving, which is Q3 times C1. Agreed? That's what's leaving. So then the balance for that bucket 1 is inflow equal outflow. So C01 Q1 plus C2 Q4 equals C1 Q3. Now do it for bucket 2 and bucket 3. Yeah, I want the equations. Again, I want the equations that govern C1, C2, and C3. So do it for bucket 2. Okay, you have 1 input here and 2 outputs. And bucket 3, you have 1 input and 2 outputs as well. Okay, so do we have the equation for bucket 2? For bucket 2, we have C. Mm-hmm. Uh-huh. Okay, correct. So whatever is coming in, what's coming in is C3 times Q2 in kilograms per second, and that's equally in some of it leaving through this line, which is C2 times Q6 plus C2 times Q4. Okay, what about bucket 3? Okay, so bucket 3 we have what? C1 Q3, correct? C2 Q4? No, bucket 3. Sorry. Wrong bucket. Uh-huh. Q2 times C3. Correct. That's correct. Okay? Can be any simpler, right? Okay. So now you write these equations, inputs equal outputs. Great. Let's clean them up a little bit. I'm going to substitute whatever I have a number, whatever I know, and then I can see my system of equations showing up with only the unknowns being C1, C2, and C3. Okay? Now, it looks like crap right now because it's not arranged properly and cleaned up. So typically what you want to do, as you probably know, is move all the unknowns to the left-hand side, and everything you know, you put it on the right-hand side. Okay? So for the first bucket, or the first equation, we have 3C1 minus 3 half C2 equal 50. For bucket 2 is 4.5 C2, etc., equals 0. And for bucket 3, minus 3C1 plus 3.3 C3 equals 0. Now, all my unknowns, C1, C2, and C3, show up linearly in all the equations. They're not squared, they're not cubed, they're not under transcendental functions or any complicated function. So they all show up linearly. This is indeed a system of linear algebraic equations, a system of linear equations. Okay? Now, we want to solve this system, and you could put it into your calculator, etc. We're going to learn how to do it with Python. And the first step, once you see a system of linear equations, the first step is to convert it to matrix form. Now, who is iffy about this? Do you know how to go from this to this? Do you not know how to go from this to this? Do you know what I'm talking about? Is this weird going from here to here? Okay. If it is, shoot me a message, and I'll send you some resources to just relearn some of the matrix conversion. But what we're doing here is when we're trying to formalize how we think about systems of linear equations, and the easiest way is to write them in matrix form. That's the classic linear algebra way. Matrices are really powerful tools to think about linear systems, because once you write it in matrix form, you've separated the unknowns from what we call the forcing terms on the right-hand side from your coefficients that control the system. These coefficients are essentially determined by the connections, right, that are built between the different terms. So if you think about it, these coefficients here, 3, minus 1.5, etc., have to do with all of these flow rates. And everything on the right-hand side has to do with what is known in the system, your sources in the system. Now, the way I think about a matrix, every time I see a matrix, I immediately think this is coming from a system of linear equations. Every time I see a matrix, I know this is coming from a system of linear equations. There's no other. I know some people represent tensors as matrices. That's only a representation. A tensor is not a matrix. Okay? So whenever I see a matrix, it must come from a system of linear equations. It's trying to solve for something. Each row in the matrix represents an equation. So this is equation 1, or bucket 1, equation 2, bucket 2, equation 3 for bucket 3. You can rearrange them, I don't care, but each row represents an equation. Okay? Now the columns represents the variables. So this column corresponds to the first unknown, so the columns represent the unknowns. So this column represents the first unknown, C1. This column represents the coefficients controlling the second unknown, C2. And the last one is the unknown, C3. Okay, how do I know this? Why does this relate to this? So how can I recover equation 1 from this system? It's simply the dot product of this vector by this vector. You know how to do dot product. So if you take this vector 3, 1.5, 0, and dot it with C1, C2, C3, you're going to get 3C1 minus 1.5 C2 plus 0 C3 equal 50. So you get this one, 3C1 minus 1.5 plus 0 C3 equal 50. So that's why I said 3 corresponds to C1. That's the first unknown. 1.5 corresponds to C2, and 0 corresponds to C3. For the second equation, again, it's the dot product of these coefficients by this vector. So 0 times C1 plus 4.5 times C2 minus 1.3 times C3. So you get this equal to 0. Okay? And now, why I like to think about it this way, because when the system gets much bigger, you can lose. This is a small system, 3 by 3. You can lose track of things. There's another important thing to consider here. I have 3 equations and 3 unknowns. Okay? So isn't that a condition that we can solve a system? You need to have as many equations as there are unknowns. Now this in matrix world, we require that the matrix to be a square matrix. In other words, same number of rows, same number of columns. Rows are equations, columns are the unknowns. Okay, rows, if you want equation 50, you just look for row 50 and see, okay, what is equation 50? You get the coefficients for that. Okay, great. So we will use the following nomenclature with or without a bracket. We're going to call the coefficient matrix A, just kind of standard practice, and we will call this the solution vector. We're trying to find C1, C2, and C3. We're going to call this X. You could call it C or whatever. Anything that's in boldface designates a matrix or a vector. Okay? And finally, the right-hand side vector, which I refer to as RHS. So next time when I tell you, okay, what is the coefficient matrix of your system of equations, you give me this. What is your right-hand side vector? You give me that. What is your solution vector? You give me this. You might put your solution vector C2, C3, C1. I don't care. As long as you know that the first solution corresponds to bucket 3 or bucket 2, and the second one corresponds to bucket 1, etc. But once you set it out, once you set it in whatever form you want, whatever order you want, just stick with that. Because when we find the solution, when we find this solution, our purpose is to find X. So now we can have AX equal B. Our purpose is to find X. The order inside X matters, because if you put them bucket 1, 2, 3 versus bucket 2, 3, 1, the order in the solution vector is going to matter, because that's what you're going to tell your client or your boss, that, okay, the concentration is bucket 3 is this and this and that. All right, so we write this in as AX equal B, and you've probably used or you've seen that, oh yeah, the solution is A inverse B. Okay, now where does this A inverse come from? It's just very simple, okay? So we're looking for X, right? AX equal B. If you take the analogy with a single equation, where A is not a matrix, just a number, and B is a number, AX equal B, then you say X equal B over A, or B, or the inverse of A times B. Okay, but in matrix world, you can't do this. You can't have you cannot divide by a matrix. It's undefined. We don't know what the division by a matrix is. In fact, 1 over A is represented generally as A inverse. Okay, so that's why we call it the inverse. It's simply like doing B over A, okay, in a single equation. All right, it's getting a little warm. Weather control is working. Okay, great. So now our purpose is, the purpose in this chapter and in this chapter, part of this unit, is how can we solve this system? How do I find X? If I'm given A and I'm given B, how do I find X? And you might say, oh, I use Gaussian elimination. Sure, you can use Gaussian elimination, but you cannot do it by hand for 100 by 100 system or for 1,000 by 1,000. We're going to use Python to do that. So the purpose of linear solvers is to do one of the following. Directly find the inverse of A and then convolute it with B. So we find the inverse of A multiplied by B. We're going to do this in Python. Or find an approximation to the inverse of A. Sometimes A is hard to invert, so we find an approximation for it. Or solve the system without even finding the inverse. Okay, these are called iterative solvers. Okay, so linear solvers do any combination thereof. So we're going to learn a few tricks here. So mostly we're going to be focused on finding the inverse of A, and then if we have time, we will touch on iterative solvers a little bit in Python. Okay, but what's more important for you, and like for a lot of the cases you will be dealing with, is solving this system, either finding the inverse or like equivalent of Gaussian elimination for this with Python. All right, so the brute force solution is Gaussian elimination, and we call this a type of direct solver. This directly solves the system of equations, and specifically what I mean by direct solver, this is a solver that has no error at all. There's no approximation error in it. It solves the system exactly. The only error you will see with a direct solver, so if you go, the methods we will be using, or it's like doing Gaussian elimination or finding the inverse, these are, and if you use a direct solver, these are exact methods. They'll give you the solution exactly. The only error encountered are round-off errors. So errors of approximating a rational number and chopping it at some point, that's a round-off error. That's the only type of error you find in these solvers. Otherwise, they will give you the exact and correct solution, okay? So there's no approximation or error or any other types of errors involved, okay? Now you might still have your system of equations might be wrong, but that's a modeling error, that's a human error, that's your error. It's not a numerical error, okay, part of the solver. Okay, so we will be using built-in solvers in Python to solve most systems of equations. We will show that this is very effective for small systems, and in my experience, about 90% of our students will actually only deal with relatively small systems, like maybe on the order of hundreds of equations, 500, 700, maybe 1,000. Anything beyond that, you will need something more powerful than the methods that I will teach you right now. Okay, next I introduced Pythonification. So I came up with this term about 5 years ago, and it's Pythonification. It's essentially the conversion of a mathematical formula or abstract concept into code using the Python programming language. So for example, Professor Saad asked us to Pythonify a system of linear equations. So when I tell you next time, let's Pythonify this, means let's grab our Jupyter notebook, turn our math into Python code, okay? Or you could Pythonify your life, which is the interpretation of everything in life as though through a Python lens. For example, when sitting at the dining table, Josh said, From kitchen, import dishes. For dish in dishes, when his mom interrupted and said, will you stop Pythonifying our dinner, please? That'd be like a really cool family if the mom and dad do Python and your son is doing Python too, and like, stop using Python. Anyway, this is a very nerdy family, very nerdy. Okay, so let's Pythonify this. There are two popular routines that we will use to solve systems of linear equations. Both of them come from NumPy. NumPy is a great library for numerical things in Python. We love it. We're going to use it a lot. I hope it stays forever. By forever, I mean like 10 years before something else replaces it. So the first method is called solve, and it comes from numpy.linalgebra. So within NumPy, there's another library focused on linear algebra, linalgebra. Linear algebra for solving systems of linear algebraic equations. Okay, linalgebra. .solve. And solve takes two arguments only, A and B. What is A? What do you think? It's the coefficient matrix. And what is B? It's the right-hand side vector. Okay. Before I show you how to build A and B, let's just kind of see how this looks like from numpy.linalgebra import solve, or you can just say import numpy as np and say np.linalgebra.solve. And then let's say you somehow build A and build B and simply say my solution vector x equals solve A comma B. Couldn't be any simpler, right? That's how it is in MATLAB as well. The other option is to find the inverse of A. And again, from linalgebra, you call the inverse of A. Now that gives you the inverse, okay? So you compute A inverse, and then you convolute A inverse with B. So that's the matrix vector product. So you take a matrix, A inverse is a matrix, and then you multiply it by B. Now to do that matrix vector product, you use the symbol at in Python. Okay, use the symbol at. Now, when would it be advantageous to use this method over this method? So suppose I go back to this example here, okay? And I have this set up, but suppose I want you to find C1, C2, and C3 for 500,000 combinations of Q1 and C01. So I'm going Q1 1, 1, 1, 1, 2, 1, 3, 1, 3.1, thousands of combinations, 500,000 of them. Think about what happens here. This input here is a known input. And from what I explained a little earlier, this doesn't show up here and doesn't show up here. It only shows up in the right-hand side because that's a known. The right-hand side contains everything that you know about the system, or all the inputs, or all the forcing things that are happening in the system. So when you look at this system, this input here, 5 times 10, shows up only here. Doesn't show up anywhere here. Doesn't change any of this. So however I change this, the only thing that will change is the right-hand side. The coefficient matrix will not change. Agreed? Because the coefficient matrix has nothing to do with the input. It has to do with the structure of how these are connected. This is a known quantity. Even if I had a known one coming through here, it will always show up on the right-hand side. Why? Because we separated what we don't know on the left and what we know on the right. So if I'm changing anything I know about the system, if I'm changing anything that's known unrelated to the variables or the unknowns, it will only show up on the right-hand side. That means that the coefficient matrix does not change. So if I'm trying 500,000 combinations of these to find the perfect C1, C2, C3, the only thing that's changing is the right-hand side. So it will make sense to compute the inverse once and just apply it 500,000 times on the right-hand side, rather than every time solving the system over and over again. Why? Again, let me just explain this a little bit more. So this solve A comma B, inside it, it's doing A inverse and A inverse times B. Doing it in one shot. But what if I don't want to do A inverse? Oh, A inverse is costly. Computing A inverse is costly. This is a 3 by 3 system. If you're dealing with 100 by 100 or 1,000 by 1,000, Every time you do A inverse might take 60 seconds or 2 minutes. Apply that 500,000 times, that's 1,000,000 minutes. How is that? What is that in years or days? Right? That's a lot. Okay? You'd probably cut that by 50, 60% if you just compute the inverse once and only apply A inverse type B. This is a fast operation, matrix times the vector. Okay? Even if the matrix is big. See the sense here? So in your homework assignment, you'll have a question like that. I'm going to change things in the system. Think about the system. Am I changing things I know about the system? Are we only changing the right-hand side? Or are we changing the coefficient matrix? If your coefficient matrix is not changing, it makes sense to just compute the inverse once and just apply it on the right-hand side. Okay? There are exceptions. Like in computational fluid dynamics, I can't even compute the inverse. It's impossible. I have, like I said, systems of 1,000,000 equations. And if I estimate the time it would take, 700 years to compute the inverse on a supercomputer, so it's not worth it. But for even 100 by 100 or 200 by 200, you can compute an inverse. Compute it once and apply it over and over again. Okay. Okay, so far I've given you, we've Pythonified this, we learned, I guess, how to solve an inverse, how to solve these systems. We need to learn how to put in A and B. How do we type them in? Okay, for small systems, and I say relatively small systems, because it's all relative, but it's actually an absolute number. For small systems, I would say less than 50, 20 equations. You just put this by hand, type it by hand. For larger systems, there's two situations. If you are deriving the system of equations from a known differential equation, like the heat equation, fluid flow equations, pressure equation, etc., the coefficient matrix has a repetitive structure. And we know how to build this with a few lines of code. Okay, I'll show you this in a little bit. The only other exception for a large system is when you have just like a weird system that is built one equation at a time. There's no wisdom in it or reason in it. And you have to, I can't think of any example like that. But maybe something from economics, for example, where there's a lot of ad hoc formulas you're applying, and you have to input every equation by hand. Then you have to type it by hand, or you could put it in like you could put the coefficients somehow, program them in a file, and just import them. But the two important cases for engineering, if we're dealing with small systems, just type it by hand. For any of the larger systems, they will be repetitive. So you'll put a recurrence formula to build the coefficient matrix. All right? Okay, so how do we build this? It's really simple. For small systems, again, it's really simple. All you do is put your matrix as list of lists. Remember the list in Python? It has these square brackets. So the matrix, you can represent it as a list of inner lists, where each row or each equation is a list on its own. Okay? So you open the outer bracket, that's my matrix. But then the first row is a vector, 3, 1.5, 0. I put it on its own list. And then I put a comma. The second row, I put brackets as well. And I put whatever, 0, 4.5, minus 1.3, and so on. Don't use numpy.matrix or some of these weird things. They don't work here. Okay? Just use this approach for small systems. It's easy, it's clean. And what's more important to me is that it looks like the matrix. I can see 3 minus 1.50, right? It looks like the matrix. And then the right-hand side, also just a simple list, 50, 0, 0. All right, that's it. Python does the rest for you. It's really good at doing that. You can do this for 10, 20 equations. Just type them in, okay? I will make you exercise that in the homework. You're going to have to put in a few. It's not that bad. Once you put it in, especially if the matrix, coefficient matrix is constant, then it's not a problem. So then finally, the Pythonification looks like this. Import solve or import NP, whatever, and then build the coefficient matrix, build the right-hand side, find the solution, solve A, comma B, or you've built this, do the inverse, and find the result. Now, what is our sanity check? Is to make sure that this result is equal to this result. right? Because this is one way of doing it. This is another way. We want to make sure that they are consistent. It's the same system. They should be consistent. All right, let's do this in Python. Okay. Get your Jupyter notebooks up and running. How many of you have seen this? Raise your hand. Raise your hand. Okay. Okay. So you've seen this. You know how to do this. For those who haven't, hopefully this will be helpful. For those who have, it's a reminder, and it's good to learn it the correct way too. I'm just joking. Oh. All right. So let's create a new notebook. Don't do a console. Notebook. What? Like seriously, Safari, it's like it's blocking my new notebooks. It's like the first day it's working with me. I've worked with this laptop for 5 years, and I allow all pop-ups to show. I wanna be spammed with all advertising, and it's not allowing me to create like the window for Python. Every time you want to change something, Apple wants to control your behavior. Okay. So we're going to move this here. Again, I am not putting text here. My apologies, but I don't have time for this. But maybe I'll just copy this here. And, oops. So this is a text cell. Okay, coding activity 1. Let's just put this 6400. Cancel. Don't delete anything. Okay. And the question is, so just to show you what to expect on your homework. So this is text that I'm copying, pasting from my solution. And all right, this is what it needs to look like. Once you're putting in math, if you're putting in your solutions, you need to make them look like LaTeX matrices. How do you look at the cheat sheet we have on LaTeX? There's 3 cheat sheets on the Canvas files directory. There's a ton of them, and if still that doesn't work, Google it, put it in GPT. It will just give you a simple LaTeX. Just put it in and move on, okay? Edit the coefficients in it, like don't put random coefficients in there, but edit it so it reflects your solution. But I need to see clean math. Okay, I promise you will be a little lenient in homework 1. So to tell you like, yep, this is not gonna fly, but next time it's not going to be acceptable. And for your own sake, for your own career, for anything you're producing, make it as clean as possible. Make it as you would expect it from a textbook, okay? All right, so let's get started with our first method. So I'm going to, we can do it in any number of ways. Let's import NumPy as MP, because that's usually just our standard boilerplate. And we want to put this guy in, so I'll guide you through this with the first we build the coefficient matrix. So first, build the coef matrix. And that's going to be A. What I do, I open 2 brackets for the matrix. I put the second bracket down. Okay. And then the first row, oh, what is this? This is wrong. This is not the correct, sorry, that's not the correct. Let me copy. Well, who put this here? Okay, let me copy this from the notes, from my notes. Hold on. Let's fix this. Okay, so begin B matrix, begin B matrix. Okay. This is correct. Okay, so I got 3 comma, minus 1.5, comma, 0.0. Okay. Hold on. Okay. And then for the second equation, so go on a new line and kind of put a space so that they look like the matrix. We got 0.0, comma, 4.5, comma, 1.3, and then finally minus 3.0, 0.0, and then 3.3. And then we're done. So I'm going to close the bracket here. And it's nice. Jupyter Notebook kind of tells you which brackets match, which brackets are matching. Okay. And then my B, the right-hand side vector, right-hand side vector, I got 50.0, 0.0, 0.0. Okay. Shift Enter, I'm done. Now we're going to do method one using solve. So I always use the following variable for my result. I call it result, just so that I know this is my result. You can call it solution. If you start calling X, C, and your notebook starts growing, you'll start forgetting what you're doing. Okay? I'm not going to judge you for that. Use whatever nomenclature you want to use. I like to be as explicit as possible. I have variable names in our code that are like 50 characters long. Okay, because I have so many complicated and convoluted variables. And with autocomplete, I can pick up whatever variable I want, but as long as I'm clear about my variables. So result is going to be np.linalgebra. Now here's a little trick. If you forget, as you're typing this, lin, and you press tab, it gives you suggestions of what's under NP or NumPy here, or whatever, SciPy or math. Here I'm looking for linalgebra. It tells me this is a module. Okay, that makes sense. That's another library that contains stuff. And then I want dot, what is it? Solve. So I type solve. So, okay, so let's say dot S, and then press tab. You have S log dat, and then solve, and then SVD. No, I want solve. That's what I want. Now let's say you forgot what solve takes. You open the parentheses and then press Shift Tab, and then that gives you what that function does in Python. Okay? So tab to autocomplete variable names or what's inside a module or a library. But then once you hit your final function that you want to call from that module and library, you can press Shift Tab right behind the parentheses to see what it looks like. And this is what this is telling me, that numpy.linalgebra.solve takes A, comma B. A is a linear matrix equation, and then this computes the exact solution X of the well-determined full rank matrix, AX equal B. Okay? So B is the right-hand side, A is the coefficient matrix. Very good. Okay, happy? So I'm going to put A, comma B, and then print result. Yay, I got 19.18 and 5.04 and 17.44. What are the units?
Concentration. Yeah, result for concentration, right?
Mm-hmm.
So,
Yes. Okay. So these are the, and what is the order here that I chose? C1, C2, and C3. Okay? C1 and C2 and C3. In that order. Now, if you change the order, that's fine. You can put maybe C2 here and the second one is C1 and the first one is C2, as long as you are clear that concentration in bucket 1 is this, concentration in bucket 2 is that, etc. Yeah? Just be consistent. Okay? That's why it's important to write the math, and then when you Pythonify, make sure it reflects the math you wrote. Because you can always go back to the math you wrote, you can see it. Okay, I put C1, C2, C3 in that order. Why is B messed up? What if you make a typo and you put 0, If you put 0, 50, you might put 0 and then 50 here, right? It's going to mess up everything. You're going to change everything, okay? And like you get a different solution. Then you come to me, it's like, I'm not getting the same answer as my friends are getting. I'm like, where are your equations? Well, I don't have them. No, go write your equations first. Then you look at your equations, you check each and every, oh yeah, I made a mistake here. We fix it, and then most of the time it's something simple like that, okay? So let's use the other method now, method 2, using A inverse, okay? So A inf is equal, and do the inverse method now, mp.linalgebra dot inf, if there's only one, and then inf takes only a coefficient matrix, a matrix A. Okay, you can read, given a square matrix A, return the A inverse satisfying the dot product equal to the identity. So, okay, so I'm going to put A here. That gives me A inverse. I can print A inverse to make sure it's a matrix, and should be of the same size as A, right? Should be a 3 by 3 one. I can print it. Oh, okay, 0.3, whatever. I don't know what those numbers mean. They're just the A inverse. Okay, now finally my result 2, my second result, or result from inverse is equal to A inverse at B. So I'm convoluting or doing the matrix vector product of A inverse and B to give me the solution, and then print result from inverse. Now this result from inverse should be the same as that one. Indeed it is. Okay? Because linalgebra.solve internally is doing A inverse and multiplying it by B. It's doing two things in one shot. But there are situations where you just want A inverse once and you're only changing B, so you compute A inverse once and just apply it on B over and over again. Very simple. That's literally all you need for linear systems of equations. The rest, or the harder part, is obtaining those equations, which you will need to do as you learn, as you get better at the physics, okay, as you get better at understanding systems, how to write governing equations, etc. Your homework assignment is going to exercise all of that for you. You have 2 mass conservation problems and 1 Newton's law problem, where you're balancing forces and a bunch of parachutists flying in a terrible way, like 7 parachutists flying on top of each other. It's like very not a good idea. But so anyway, so that exercises where these equations come from. Okay. I would say you can just pack and go home, but unfortunately I have to teach you a little bit more theory and more in-depth stuff. Okay. Let's resume. That's for the YouTube, so I can know where to cut. In general, systems of linear equations are written for a large number of equations, and you should have as many equations as you have unknowns. The general nomenclature we write is that the matrix has 2 dimensions in it. There's rows and columns. So when you are trying to access a matrix or talk about a matrix, talk about the coefficients in this matrix, to find your way around the matrix, you need 2 indices, 2 numbers, which row and which column. It's like when you're trying to find your location on a GPS map, how much north, south you want to go, how much west or east you want to go, okay? So 2 numbers. Same thing with matrices. And in general, when we talk about matrices, we talk in abstraction about the coefficients in the matrix. And they're represented by 2 indices. We call them A. So the first entry is A11, and then A12, and so on. You got a bunch of these coefficients. Here, let's clean it up this way. So in general, a system of equations, of linear equations, could have m equations and n unknowns. So it could have m rows and n columns. Okay? And you can tell the number of unknowns either from your solution vector, x1 through xn, you just count them, or the number of columns. The number of rows is how many equations you have. Okay? Now, in general, you can also write this as, like I said earlier, each equation is a dot product of the row and the column. So equation 1 is row 1 times the dotted with the solution vector equal B1. Equation 2 is the second row dotted with the solution vector equal B2 and so on. So this is what this means. This is the representation of a dot product, the summation of the coefficients multiplied by your solution vector, right? A21 times x1 plus A22 times x2 and so on gives you B2. I here in this equation is the row or equation number. We rarely have to use this, but this is just the generic representation of a matrix. If you're doing matrix algebra and you're doing things with matrices, you have to use this notation so it can simplify the math for you. But the two indices under every coefficient represents, the first one represents which row you're at, and the second index represents which column. So for example, in this first row, the first index is always 1, A1, 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 A1. And the second index is the column. A11 is row 1, column 1. A12 is row 1, column 2, and so on. A1n is row 1, column n. And then, AMN is row m, column n. Okay? And they call this AIJ. I is the row, J is the index. But if you're like me and you forget things, and I don't like this notation, I call it, instead of calling it AIJ, I call it ARC, arc or A row column. Okay, so the first index is row, the second index is column. Okay, if you forget what AIJ is, just call it arc, ARC, row, column. First index is always row, second index is always column. Now to be well posed, the relation between M and N, we already mentioned that, is that they have to be equal. For this system to be solvable, even remotely solvable, you have to have as many equations as there are unknowns. In other words, as many rows as you have columns. Okay, so M and N need to be equal. That leads you to what we call square matrices. And for a square matrix, for a well-posed system, you have as many rows as you have columns. So the last term here is A and N rows and columns for N equations and N unknowns. Now, once you are in matrix world, you will notice in working with engineering systems or in science, in nature, in networks, in electronics, that you will see different looking matrices. This would be a general matrix. We call this a general dense matrix. Most of the coefficients are non-zero. It's full everywhere. There's every row. There's an every row has most of the unknowns non-zero. You could have upper triangular matrices where you have full equation for the first row, one less unknown for the second row, and so on. And then the last equation, you just have one unknown, one coefficient for the unknown. You could have a lower triangular matrix. You could have just a diagonal matrix. Okay, just only the main diagonal contains coefficients. You could have the identity matrix. And you can have banded matrices. So this is going to be very important for heat transfer, mass transfer, fluid mechanics. In banded matrices, you have a few non-zero diagonals. You could have 3 non-zero diagonals, 5 or 7 non-zero diagonals, and they're called banded matrices. Okay, so this is kind of about matrices. Okay, now what now? For small systems like order 100 equations, or for systems where knowledge of the inverse of the matrix is important, just use the method, what we did, and move on with your life. And that's going to be okay. You don't need fancy iterative solvers or the solvers I talked about earlier. If you end up taking our advanced computing courses, we will teach you about those there. If I teach my computational fluid dynamics course and you're interested in that or you're doing research in that, take it with me and I'll teach you about iterative solvers there. I have some extra slides at the end of these slides to expose you to some of that. And then, you're good. But before we say, okay, we're done, I want to give you an example of a large system of equations and also wet your beak a little bit about how to solve differential equations. So we are going to solve a differential equation without teaching you how to solve it and just give you the formulas that you need. But then you will see that, oh my goodness, this is really powerful. And then suddenly the number of equations can explode very, very quickly. Okay? So far we worked with small systems. Let's work with a larger system. And the simplest system we give is a one-dimensional, who likes heat transfer? I like heat transfer because I like to stay warm when it's cold. And when it's hot, I want the heat to move away from me, so I want to be cool. Heat transfer is very important for life and everything. So I hope that's enough motivation to study heat transfer. But this example is going to explain to you or motivate you that, yes, indeed, beyond the simple example I gave you in the mass conservation, there are systems that will result in hundreds of equations. And this is also an example, what I said earlier. We are going to take a differential equation, convert it into a system of algebraic equations, and now we know how to solve those, and we're just going to solve those. And also we learn a few Python tricks. Okay, there's a lot going on. Okay, so I want to remind you a little bit about the first derivative, the example we did in the first 2 lectures, where we took a first derivative and approximated it as rise over run, or f of x plus h minus f of x over h, where h is really small. You can apply this on a system of points where you have data at specific points. So assume you have the function at these specific points, and these points are all equally spaced, and the spacing is h, and you want to evaluate the derivative at some point xi, then simply the equation applies, fxi plus h minus f at xi over h. That gives you the derivative at xi, okay? Or in other words, this is fxi plus 1 minus fxi over h. Don't worry about that. But the point here is that the same way we can do a first derivative, we can also do a second derivative. I haven't given you this formula. You might have learned it. Don't worry about it. I will give you this formula. I will tell you a second derivative is approximated as such with 3 points. So the same way we apply the first derivative, we can approximate the first derivative. We can approximate a second derivative. Why do I need that? Because I want to convert a differential equation, a second order differential equation, into algebraic equations. Okay, so let's see how this works. We are going to consider the heat transfer in a rod or in a one-dimensional material. So it could be this wall over there, or that wall, or that pipe across the pipe from bottom to top. Okay, assume it's only one-dimensional. There's no heat going sideways. It's going from inside the room to outside the room, or from the bottom of the pipe to the top of the pipe, and there's like just one block of material from the bottom to the top. Okay, so we call that a rod, subject to fixed temperatures on each side. So there's a temperature on the outside, the sun is shining, the temperature is probably 85 on the wall on the outside, and the temperature on the inside is 70. Now I have insulation material in that rod or in the wall, and heat is going to do something. Because that insulation material is trying to prevent the hot temperature from the outside to kind of come into the inside, and we want to study that. We want to analyze how the heat moves from one side to the other. Okay, so we draw this beautifully like this. I will call this location x equals 0, this location x equal L. So my system, the rod or the object is of size L. Okay, it's just of size L. We use x to designate our coordinate. It's just simple in the x direction. And I have fixed temperatures at each end. I call this T at x equals 0, or T left, L, and T at temperature at x equal L, T right. That's given. We know this. That's a given value. You can measure it, or you can specify it yourself. Okay? Have your spatula on the grill, right? So the temperature, and like you forget it on the grill, or you forget your spoon in the pot, and the temperature of the water is boiling temperature, the temperature on the outside, and then the heat is gonna propagate throughout. Okay. So that's the situation. You know the temperatures at each end. Now at steady state, the heat equation, I want to do one more thing, okay, before, okay, let me go back, because kind of like a punchline. Okay, so now I also want to complicate this a little bit, okay, because the solution to this problem for a uniform material is simply a straight line for the temperature. You will learn that. If you didn't learn that in heat transfer, you will learn it again, hopefully next semester. So I want to spice this a little bit, and I'm going to throw a wrinkle in this, and I'm going to put a heating source in the middle of the rod. Okay? So suppose that I have some heating element or some electrical wire in the wall and that they're getting hot, and they're changing how this is being heated. Or you have like your spatula or something and you're blowing a hair dryer on it, your hair dryer in the middle. So it's either adding heat or cooling it. It's doing something to it. The equation that governs the temperature in this rod, so obviously here if I'm heating it, this is gonna, and these temperatures are lower, it's gonna get hotter here, I'm gonna have a little peak here, and then it's gonna drop off. I don't know how it's gonna drop off. Okay, that's what we are trying to go after. But what I know from first principles is that the governing equation for temperature in this system looks like this. The second derivative of temperature in the x direction, so d2t by dx squared, is equal to minus 1 over k times this source. Okay, so what is k? K is what we call the thermal conductivity of the material. It tells you how good this material is at communicating heat. If you have a large K, a large thermal conductivity, it means you conduct thermal energy faster, better. If you have a small k, you conduct your thermal energy much lower. So why do we that's why we vacuum double glazed windows. We vacuum them because vacuum has almost zero thermal conductivity, or a much lower thermal conductivity than air. Air has a much lower thermal conductivity than water, which has a lower thermal conductivity than oil when you boil oil and cook with oil, right? Has to do with thermal conductivity, how fast can you move heat across, okay? So the smaller the K, the more resistive the material is going to be to transfer the heat from the sides and from the source. So I don't know, with a small K, maybe we're going to have a very high peak in the middle, and then it's just going to drop off quickly. With a larger K, it might look more like a parabola. Those are questions we're going to ask when we solve this problem numerically. Okay? Now, S of x is a source that I'm putting here. This is an energy source. Could be a lighter, could be some fire, could be, again, your hair dryer. We can measure the thermal energy from there, usually from the specification of the fuel that you have, or you can measure it just from the heat flux that's coming in. The point is, I know what S of x is going to be. So I know that's my source term. I know it. I know what K is. That's the material I used here. And my objective is to find the solution to this. We're not going to do this analytically. You might be able to do it if S is simple. If S is complicated, you can still do it. You just integrate it. We're not going to do that analytically. We want to do it numerically. It's easier and faster. And you want to do it analytically, great. You can have more verification for your solution. Okay. So again, this K is called thermal conductivity. It's got units of watt per meter Kelvin. And the source term is watt per unit volume, or energy per unit volume. So for example, from the sun on a standard day, you go out, you get about 1,400 watts per square meters from the sun. Okay? Okay. But in this case, it's volumetric in the case I gave you, not on a per unit area. Okay, I'm out of time. We will resume on Tuesday. I know you're like all focused and I'll repeat this on Tuesday. I'll repeat this so it gets fixated in your brain. But get started on your homework. It's due next Thursday, please. If you have questions, be happy to answer. Do the help sessions. Shoot me a message on Canvas. And make sure you catch up because we're going to pick up real quick. Okay, we're going to pick up real quick in the next few weeks. Okay? So thank you and Godspeed. Have a nice weekend and happy Labor Day. Go and labor.